All right. Yeah, it's my pleasure to introduce George. He's an associate professor of computer science at Brown University, directing the Intelligent Robot Lab. His research focuses on building intelligent, autonomous, general-purpose robots through abstraction hierarchies for planning. He's made key contributions to state abstraction and hierarchical reinforcement learning. And actually, I feel like my work has been super inspired by a lot of his stuff. So it's really a pleasure to be able to have him and hear him talk. And so, yeah, he'll be presenting on reintegrating AI, skills, symbols, and the sensorimotor dilemma.
Thank you, Helen. That's very kind. Okay, so before we begin, I'm just going to talk about reinforcement learning beyond rewards. Actually, my focus is kind of going to be on reinforcement learning beyond reinforcement learning. So one of the things I'm going to be talking about is how we can take reinforcement learning as the baseline technology that underlies interpretation, but then we're going to try and sort of understand the mathematical principles which will let that agent build models that lets us access the rest of AI. Okay, that's what reintegrating AI means. I'm trying to find a coherent story of how we get all the things in an AI textbook like Ross and Norwich, how all those things arise, where if you start with the reinforcement learning agent at the bottom. Okay. So we're kind of after the sort of foundational math or piece of science that explains how everything gets put together again. And I'm going to start with the basic assumption, which many of you may or may not share, which is that humans are robots, not computers. Okay, so I think that the idea of an agent is underspecified, and we need to let it go a little bit. If you look at all natural intelligence in the world, none of them are just brains. But a computer is a computational artificial analog of a brain. There's no brains in the environment. There are no brains like hanging off trees or swimming in lakes or found in fields. You only ever find brains inside skulls, which are in bodies. Okay, so all intelligent creatures in the world are creatures. They are not computers. And so that means that I think we should take very seriously the idea that a general intelligence should look something like a robot. And when you examine a robot, what you find is that there's a crucial way to differ it from a general reinforcement learning agent that we might find in the world. So when you go to a reinforcement learning agent, that needs to solve one task, what should be do is you pre-construct a frame for that agent that contains a description of a state space and a description of an action space. That is possible. Clearly, you might describe a goal lane agent as having a state space of all robots and an action space of all the moves. And similarly, you want to have one diagnosis diseases in X-rays, you might say single spaces are images and alpha spaces are disease or no disease. But when you're talking general intelligent robots, you don't get to do that. You always have to deal in a much more complicated basic sensory space. And you have to solve all the problems in that sensory space. And that's pretty crucial to what it is to build a generally intelligent agent. You need to be able to solve all these problems in the same very complex input and output system. Okay? So you need to be able to do all these things in one robot reasonably well. So the model we should have at the basis of general intelligence looks like this. Very complex robot getting actions in the world and receiving a very complex signal back. That's what happens if you buy a robot and you deploy it, you switch it on, you find that you get some sensors at some degree, and you can get some actions at some degree, and those are fixed, and that's all you get out of the box. So if we want to formalize what a generally intelligent robot would look like, we would say, well, it's got some very complex observation action space, and then we're going to hand it task after task. And each task is going to be formalized from a distribution of tasks, and we're going to formalize as a reward function. And then if we put that reward function together with the observation action space, we get this, which should be familiar to you. This is the general decision process performance. It looks like an MPE, except that there's no marker assumption. That's obviously wrong for it's the action function of robot history and the reward functions of robot history. And this is just this is just a very formulation of what a robot does. Okay? This reward function is called as a theorem, phenomenon Morgan's term, which says that if you've got any preference of the behavior relation, you can write that on the third function. So we can definitely formalize the general intelligent robot. It needs to solve a wide range of tasks this way. And the interesting part about that robot, again, is that it needs to solve more in this very overblown input and output space. So the core is that you want to do now. If you want to solve 52 Atari games, you can't make those games inputs be positioned to players or the number of circles on the screen, or how many layers there are, you have to input pixels. Because that is a power interface to contain all of these state spaces of all the tasks you might wish to solve. Okay, and the output space, so the first thing is that is you control all the games you want to solve. And if you want to do something more complex than a target, you need to expand this action space. Okay. Similarly, if you want to learn to play chess in a generally intelligent robot, you don't get chessboard as an input, you get pixels, in fact, you get HD video running at 30 hertz or 60 hertz, and that contains extremely large amounts of information about there's angles, there's the texture that these things are made out of, there's the texture of the table, which is all displayed, there's the lighting, there's all that stuff happening, and it will be very, very hard to learn to play chess from this representation directly. Instead, we much rather have a drastically compact representation that contains just the information coded about chess, just input and output of chess. Really, and this is not a visual function to run, it's not a visual compression function, because all these three chess will be in the same position. Right, so I have to compress the same thing. So it's really untrue to take this HD video and use this tiny compact representation. But I think you have to do it, because what we call the Sensorimotor dilemma. If you want to build a generally intelligent agent, the wider the range of target tasks you're going to have that agent to solve, the more complex the Sensorimotor is going to need to be, because it needs to contain a union of all of the observation spaces and all the action spaces of those individual tasks. Okay, that's an unavoidable obstacle for a generally intelligent agent. That's why you and I are all. That's why we have such rich two-to-one spaces. Because we can't get over to anything else. Because if we want to solve a wide range of tasks, we have to have complex input and output spaces. And as the input and output spaces grow, as the Sensorimotor space grows, we become less able to solve any individual task. That's why it's the more tasks you want to solve, the worse you are at solving each individual problem. That's really different to how you might imagine a forceful agent being able to solve one task, where you could set a task that way. Every task that I want to solve has to be solved in the world with rich sensors and actuals. So how might we resolve this? How might we get around this? How might a general purpose agent get around this problem? One thing you do is you can just get a lot of data and you just learn that in instances. But that doesn't want to look at how we might be able to get the rest of the AI. That's just everything is an RL system. What I like to do is be able to simplify the different structure. So let's take the decision process that is the original robot Sensorimotor space plus a reward function describing the task. And I'm going to redescribe this task as a new compact decision process up there that captures just the complexity of tasks and not complexity agents, right? That's what we do when we apply RL to a single task. And in terms of we actually understand that well, this thing out here and this thing out here, we just need to do a combination computing. We need to do search abstraction, you take a complex conceptual and put that same abstraction probably you can say until something. Compress that down to small parts of the signal, and we need to do action interaction. We need to take the complex action phase that we have the agent and construct and compress it down to a small number of regular actions like image. And if we do both those two things and they're mutually compatible, then we get a decision process upstairs that's abstract. You both complete fully the MVP of the problem, and you can do everything you need to do in that problem, in that new MVP. Okay, so the sort of theme that we might have here, we might say, and the reason why it's important that this is a decision process, not a marketable decision process, is that actually this notion of decision process captures almost everything that you might want or that you might find in the narrative. Okay, if we take a decision process and we say that that decision process is observable and differential, then it's a marketable decision process. And it's also the third thing on discrete search. So if you happen to have both an abstract decision process and you realize that the deterministic known is discrete and sequential, then you can apply a stop or very close to the vector search. You read and match out the vector. Similarly, if it's active, you're in classical hand land, you have great algorithms for classifying. And if it's external, you can have zero search. Okay, so you can imagine multiple model check for saying that this model check for observable sequential, perfectly known, discrete, and serial, and then you can swap in how we get it off the shelf algorithm, chapter 7 or something like that. Similarly, if you have a decision process that is observable, not sequential, with discrete actions that are contextual banded, And if you have the same data that makes your boundary data classification, and if it's actions or overvalued, you have regression. Okay. In fact, if you go through Russell and Norbeck, you look at every single thing presented against, and the third edition was the last time I did this, so it's probably going to edit it. There's four things that occur in Russell and Norbeck. There's a decision process plus foundational structure. There's a piece of math to do, like probabilistic reasoning, which is a tool you use to solve the decision process. There's an application area like computer vision where there's something special about pixels which exploits to make these algorithms better. They're all decision processes actually, and there's advantage. So you can reach almost all of the AI enterprise by special cases in the decision process. So you can imagine the process where a robot starts out with an extremely complex instrument space. You give it a reward function, and then it's going to learn where it's going to find that that's discrete, factored, deterministic, and adversarial, and swap that out with the or it's going to be navigating through an environment. It's going to find that the best errors in that environment is actually a graph in the form of an embedded in a map, and therefore it's going to do search. Or if it's going to try and learn software, it's going to learn actions and observations that are about what software. And those are going to be continuous. There's no way around them. They can just put the various actions and maybe the policy search. But the point here is that we're matching the complexity of the actual task, not the robot, against each task. Okay, so we go with all these compatible action and observation actions. How are we going to do that? And what we focused on doing in my lab is we focused on thinking about like let's do skill-driven say abstraction. So let's say, okay, I give you the high-level actions, and then I want a specific computation performed over those. Is there a way to formalize that question, and is there a way to bottom-up construct the state abstraction such that it provably answers that? So in previous work, we thought about planning, right? If you give me a sequence of actions, can I tell you that sequence of actions can definitely be executed, or can I tell you the probability with which that sequence of actions can be executed? And you did that in 2018, so we now know how to answer that question. I'm going to show you a kind of newer formulation from my postdoc from where all we want to do is want to run development equations. So we want to get value of the development equation over the high-level actions, and we want to get the same result as if we did that on the low-level states, but we're going to involve high-level states. And it turns out that if you take the development equation, you see that most of the expectations of the distributions of states, the world approximately like this thing over here. And this looks a lot like just a plain old development equation, which sets off these expectations of the distributions of states. And so if we decide how that action, how that state should be distributed for states, and you think about executing off and landing the distribution, and you say the value of an abstract state is the expectation of that distribution, then you can do a little bit of math and you get on back up. Okay, so what that means is that you should think about an agent as somewhere between distributions of the states at a high level. Distribution of state is your abstract states at the high level, and if you write math that way, you get the development equation downstairs, the development equation upstairs, and have to be exactly the same. So that's the abstract development equation. And so you should think about an agent jumping between distributions of the states, and you choose to refine that distribution for some of the other example. You should always be able to identify which option can be executed, otherwise you're not normal. So we can construct an abstract MVP that takes this jumping between these distributions and replaces them with a collection of states, and that model is provably value preserving under some conditions. So it has all the three marker properties, and it's an MVP if the original thing was an MVP. So just to show you that here's a overall this little nasal, so we walk it to the top down view. These are the fixed states linked to the agents of RLC. It's got options moving between inside the room between the two corridors, and it's going to view the pixel extent, and we're just going to move around some pictures of stuff on the walls to add extra complexity. And what you get is walking into the space, galleries of player, and then we'll build an abstract embodied representation using primarily through a neural network with our loss function, and we'll extract the pseudo MVP that captures the graph of the map, right? It recovers the original graph And then inside that graph, it can just do like really trivial planning. And you can also ask for the grounding in any of those states. You can say, for this particular state, what's the distribution over images that I expect to see? You can draw samples from that distribution so you can visualize this agent moving from that and kind of dreaming in your head about what the agent is doing. Okay, so that's the last way. Say more interesting cases when the local actions changes in the individual state variable. Like if you've got a robot hitting something out and changes some things, not other things about the world. Then it turns out that after a little math, that kind of factored action creates a factored abstract representation, not a graph. It actually creates strips. So when you run state abstraction, if we have if the agent observes these elements that drawn at random and they describe the position of an agent poses in a hood, and the agent moves up and down like this, it can extract learn small represent each number, and then you extract the factor notion of the grid, and then inside that factor grid, it's just the factor in the new factor evaluation solve that is in it. So it's extracting the discrete factor graph out of that data from pixel data. And then as it goes through, these are hallucinated run-throughs, right? So it'll run through that abstract position, and then it will generate samples of those symbols and visualize them. So you can see that it's learned both the abstract graph structure and it's learned grounding of every abstract symbol in that graph. Okay. So just to show you the success of the robot, this final experiment that I realized. This is an experiment where we put a robot in a room. You can see the room has covered, it has a switch, and it has a cooler up there. And then I hand over some skills to this robot. So the robot can move from cooler to covered, and back again. When it's standing in front of the cooler, it can open and close the cooler. When it's standing in front of the covered, and it's not holding anything, it can open and close the covered. And you can turn that switch on or off when it's not locked by open covered. When I turn to the time, there's a light inside that cover that blanks out. It's so bright that it blanks out everything inside the cover is the robot. And in addition, there's an object you can see up here that the robot can pick up the objects in front of it and picks up this holds it up here. So if you take and then the input for this abstraction was this going to be robot poses in that, but also the entire one to show you the cool here is easy to see and the all joint states of the robot. And if you let this over execute a couple of skills sequentially and gather data, you need about 160 option executions, which take an hour or two. And we put that into our algorithm, we will construct a symbolic representation that is provably sound complete for reasoning about this task. So here's an example of the text file that generates an inarguable symbolic representation. This says if you want to navigate to the cooler, then the precondition is that the robot table must be drawn in small one. So if you draw some samples in that symbol, we'll see that it's mostly to the robot's close than that, and it's standing over there, which is in front of the cover. Afterwards, that will be show more, and symbol 0 will be true, then it's stand over there, that means in front of the cooler. And it's going to take about 37 seconds. Now, the robot has discovered a distinction between those two things. The right distinction we're thinking about this execution is learn the grounding for each symbol, and construct the text operator so that it's a kind of competing model of that operator. There's one interesting one. If you want to open the code, you should be symbol 1, which you stand on the code. And symbol 3, symbol 4 should be how the robot's joints and the voxel queries are drawn. The robot's joints, you can see small to have 10 design characters, and it's not holding anything. It means the robot doesn't have anything in its hand. And these are voxels, and you can just click the box to move the cover, and you see the cover is closed. And afterwards, the cover is open. So what's happening here is the robot has a dynamic model to say that before if it wants to open the cover, it should stand in front of the cover and not hold anything, the cover should be closed. Afterwards, the cover will be closed. But it has discovered all of those things from pixel level there. And it's discovered then to produce an operator that is fluid standing people paying for this thing, for those that text file. So if I take that text file and I put it in the class of mail and I ask it to do an object over here, in the cooler and it's covered, you'll see that the first thing does is it opens the cooler, but then it doesn't pick up the object. If it didn't pick up the object, it wouldn't be able to open the cupboard. But it moves to the cupboard without picking up it, and then it doesn't open the cupboard because the switch is on, and it opens the cupboard, it will be able to turn the switch. So first it turns the switch, then it opens the cupboard, then it goes back to get the object and places it in the cupboard. So that's the kind of thing that classical planning classically does. That's not surprising once you have this representation that a classical task planner would do that. What's interesting here is that the robot acquired that representation from pixel level data using only a given set of most clues. And no final knowledge, this is not distracted anymore. It's more there. And also that the representation that it covers is provably something completely false. Mathematically, the right representation for reasoning about this one. And then I also started looking at it takes about 500 seconds to generate this plane. Of course it does because it's a trivial representation once you pull the right one, which is the whole point. We've also done a few other things beyond the pilot. One is in advantage, and from more pixels we can learn faster than operators for this task. Assuming we were given the skills, which is sort of cheating. And then we've looked at object representations where instead of learning a single representation for the entire system focus, we get it objects. We're going to learn symbols in the frame of objects. So, just as I showed you, you can say things like this, one big one voxels. Instead, we center the thing around those objects, and we're able to do things like these are first-person view images from Minecraft. We can take those there, learn using action in Minecraft. We can learn a symbolic representation of those things in PDL. We can apply them to new Minecraft instances using a small amount there, basically relatively constant amount there, and we can use complex differential plans in Minecraft from pixels. The only thing is we have to assume that the actions are present. So remember, we're learning observation and action abstractions. And at the moment, we're studying how, if you're giving the action abstractions, you can produce the observation abstraction. This is building the top. Building the golden top, which has a bit of a hole, a bit of a fish, some tools, and it's going to go and I think it manufactures a thing, picks up that golden block and it goes and manufactures that whole thing, and manufactures the block too. The point, though, is that the properties of the high level action actually take the properties of the abstract symbol. But they actually completely specify. Once you've done the math, you see that as soon as you understand the properties of the action, everything else drops out. It's just a fairly simple machine exercise. Okay. And we've done this now on my last papers, including 6 real robots. So I think it's a reasonably well defined framework. I wanted to talk about a few consequences of this. So flipping back to the action side, I said that the properties of the actions are the most important thing. The properties of the actions completely specify the properties of the abstract states. One of the properties that the actions have to have is that it has to be chainable. So what that means is that the termination of the option has to line some initiation set of other options. That means you have to be able to execute one option, and it should leave you in a position where you can execute another option. If you don't have that property, then you will find that your abstract decision process that you built is broken, has gauges before the end. So we spent a lot of time thinking about how we build action discovery algorithms that can discover skills that are sequentially composable. Okay, so this is from my PhD in Konidaris, who's Mr. Clements at Amazon now, and he's been working on doing some fairly complex domains. So this is an example in this is the ant robot, this is an ant in a really complex maze that builds a graph where it can at one time remove to randomly generate points in the graph by essentially executing skills that were constructively connected. Okay, so what it did is it just essentially built a graph and then it's named all the elements of the graph. And it's got a training phase where it builds the graph using intrinsic motivation, like it just keeps building this graph that is wider and wider and wider, and then at runtime you can impose goals to it, you can tell it the goal is reachable in the graph, and then you can go and connect up skills that is essentially execute a particular task. And that's all conveyed within the file. Most usually there's a fair RLC. This RLC, so you can go find that with close that. Where you can scale it, images of legal skills, so one zoom the range. That one feels something that was XP. And this is another one where it does the same thing. This is just a host skill. And then second conversion that skill outside of the room. So the first skill is created because it's still that allows the second skill to execute. So these things are naturally sequentially composable. So we're almost at the point where from pixels we can learn skills that are resulting in well-formed MPs when we apply an abstract set of actions. My lab is also spent a lot of time trying to do this on real robots. In there we've been exploring a lot of structured phases in real robots. Okay, so which is not compatible with RLBrew. But if you were robots, you know, the robots can be like motion planning. Zero stop, of course, you motion planning, no need to learn that. And so, what we found is, for example, we constructed a policy box where a texture manipulation skill is surrounded by a motion planning envelope that basically makes it very easy to execute from multiple places. And so you can sequentially execute these skills zero cost. We need the decision process that we could be constructed and disconnected. And we've also both things where the actually can build a map from a robot to kind of apply the robot to space, and then you can navigate different places in that map without having to do learning. Meaning so we can obviate most of the learning process of various model representations. So the structure of the national boundaries in that map is efficiently taking a manipulation plan which doesn't talk about the robot's navigation or pose the map at all, and resolve that the sequence of these motion and manipulation actions that will allow you to like run a copy where the navigation actions, manipulation generated by the robot are generated on the fly in real time for a normal map. Okay, you just go through the map once, and then you can construct a plan. So what's nice about these two pieces of work together is that they say if you give us motor skill in this form, then zero shot we can construct the rest of the navigation step for you. Okay, so you don't need to think about maps, so that can be constructed around time. And this work here deals with what happens when you don't know the state of you don't know which objects are present in the map, so you need to go find them. So they're partially observable, the state and existence of every object. And it turns out that you can also solve those problems very efficiently using things like plan, active perception, and motion planning. So we can actually deal with partially with environments where this complete state of the environment is not known. The robot has to figure out what it needs to know about the environment in order to execute. We call it object selection problem. And coming soon, we have object-centric cross motion plannable symbols. And when we put all these things together, where we will be roughly is that if you hand me motor skills in composable interaction equivalent format, I can generate rates to set for you. I can go all the way from signal to symbol, using this to deploy that robot in an environment, and as long as the manipulation skills fault, and those are going to be any ways, including ways to tell fault. As long as those can be taught, everything else will fault. We will learn some more representation, we plan to see some more representation, we fix it in the program, it has problems that can manage it, so it is robust, or it is reasonably robust, and you can make very long range planning. Okay, so where are we in this enterprise? At the moment, we're beginning to understand the fundamental mathematics of how nature can build its own models of much more complex decision processes. Right? So an agent with a really rich input and output space and build abstract actions and abstract observations and build totally models of entities, and where the semantics of those things are all well understood, the grounding is well understood, everything is well grounded, everything you learn, you can be available in real time, and when there's an error, you can determine what it is. And mathematics is now increasingly well understood. There are still some open questions about partial derivatives. Everything I talked about is about NPs, not omnis, and of course there's no NPs involved. And we have this probabilistic semantics that these are robust. So everything there's probabilities underneath everything, there's no sets, there's no all the classical things are made, classical planning, very little is all gone away. And rails learn reasonably efficiently. We're not always getting to pixels and dots, but we're pretty close to being able to do this in a few minutes on a roll in a new class, which would be pretty cool. And so if there's one thing that I want you to take away from the talk, it's this notion of abstraction general AI. If you've got really complex input and output splits, you have to have with the robot a reasonable rest to get to the rest of AI is to build these abstract models of decision process for each task in a task-driven way that are massively compact and capture the limits of tasks on the robot, and then apply an algorithm that matches the sort of structure of those decision. And if you can do that, then you get to all the other parameters of AI. You destroy the gray elements that are involved in all those. Okay, thank you. That's all I've got. Maybe that. Got about 2 minutes for questions. Brad.
Thanks for talking. For these general abstractions, do you expect that one level of abstraction will generally be enough? Like if I think about like putting my kids' toys away, I might think of it like the highest level is this discrete thing where each toy has its place and it's either in its place or not. But then there's still a robot general abstraction of just moving objects around the physical space.
Yeah, so that's exactly right. So one of the things I didn't talk about is that actually in practice, these things will be very layered. There'll be a sequence, instead of going from the low level one to the top level one, you'll find multiple layers. And there's a couple of reasons to do that. And one reason to do that is because if you were to learn these things from scratch, you'd be learning the same things over and over again. So when you learn them in a hierarchy, you can kind of branch the hierarchy. So for example, the abstractions you use to play chess and checkers are very similar the first couple of levels, and then they branch right at the end. And similarly, you know, picking objects up and moving them around. In fact, if you look at all the technologies developed in robotics to a first order approximation, they're almost all action abstractions and observation abstractions. Okay, and one way to think about that is that is the structure contained in the world in the robot, and that the field of robotics has proceeded to exploit those things to produce good algorithms like motion planning or object recognition, and that we should layer those first few things in. They should actually be built in so that a robot can choose to learn off of them, to bootstrap off of them instead of having to start from pixels. But that's another talk. So does that answer your question? Yes.
General abstractions scheme. In which level do you plan on? Everyone?
You plan as high as you can get. Because complexity planning scales exponentially with the horizon, right? So you want as short a horizon as you can possibly get away with. And then it could be the case that you can go refine that plan through low levels of abstraction. But generally, you always want to start as abstract as you can get, right? Because this Sensorimotor space is crazy. You never want to operate there if you can help. You want to get as close to the immense complexity of the task as you or I would model if you were to give only that task to an RL agent. If you can get there, then you're good. Does that make sense? Yes, Bruno.
Question, when you said that you're modeling, that you're mapping from the original entity, one of these abstract entities,
yes,
perhaps AR,
yes.
Are you assuming that the skills you're going to have one set of skills per task? Because the reason why I ask that is because whenever I think about skills, I think about this, there's a cost to learning the skills, but it pays off because I'm going to reuse them across many tests.
Yes, yes, well, actually what happens is we'll have very cool skills already have, and then you might have to send those again. So actually, you know, I actually thought we truly abstraction that those skills can say abstraction and we can call from those. That's all. It's like a lot of learning, larger skills thing going on there. In fact, and I think that one of these things to do is they kind of have to recruit these things. At one time, and you didn't still pick something that very just add that into thing one time. The only thing that is a little tricky is that what we've shown in the map is that there's a very close correspondence between instruction and skills and structure in the state abstraction. So the skills are up to the state abstraction. The skills are opportunity to state abstraction. But one trick is one unfortunate thing is if you recruit a skill that doesn't have structure, then the whole entity loses structure. And so, I don't know how to do that, but anything in that way, it's an oscillating effect is still something that,
I have a second quick question. The gamma tau, I assume that's like the discount rate for that one. Test.
Oh, yes.
How do you deal with the question of deciding what is going to be the frequency of actions? Because in some problems, like right now, I'm just watching the stop, I have to make a lot of decisions, at least not a motor decision.
Yes. Yeah, that, okay, so the first time you go through the decision is buried inside your abstract action. That gamma tau is, I think a better way to think of that is like one mass molecule will be interrupted at every load of passing. So, you know, you're playing a video game and you know, your difficulties get so much, then, you know, the way that Sassy models are very constant, it's not all there. And I just developed that as unique, so. But I think this gamma is a load of concept and these actions, so they're all going to be varying different, levels of, they're all going to be support here, so just call it S and P. That makes sense.
Hey, Georgia, Glenn Brissett from the University of Montreal, Milan. I kind of wanted to go a bit more on Bruno's first question, because Chelsea was talking about a bit too, of being able to fine tune models, like find a good representation that's easy to learn.
Yeah.
But maybe the question that's kind of on this related to you is, so for being able to integrate in a new skill, does that become easier as more skills are partitioned into the space, or does that become harder? Like, does it scale well and become easier as more things are added?
Okay, so when you go to the NDP, you want to include the minimum number of actions, roughly speaking, the branching factor goes up, and you don't want. So, but the question you're asking is maybe if I had a larger library of skills, is it easier to learn skill N+1, or is it easier to adapt, find skills to adapt? That's probably right. So that's like never learning that you get to do source adaptation or subject source adaptation, something like that. My guess is that there's two layers of that question. The first layer is, have you learned the structure present in the robot on board? So if I say you as a doing skills and you learn the linear network and you chop off the head, it contains some compression that tells you about a manifold on which skills learned that will be useful, and that's going to get better than the skills are. And then there's the second part, which is now you've got a select from some part under the bootstrap from, and probably that gets overwhelmed if you have a large enough number of skills. So I was asking, you know, imagine if you download all the videos on YouTube and you just ask the foundation model which actions are being performed. My guess is it's probably less than 1 or 2,000 in total, and 80% of the probability density in the first two. I think there's not actually that many. But that's, you know, that's uninformed front. So,
Yeah, thank you.
all right, I think we're, thank you.
Yeah. So